Hi, I'm John Carl Wharton. Have you ever wondered why cars and buildings only have square, rectangular windows, but airplanes have oval-shaped ones? Today I'm going to answer this question by explaining the effects of flaws such as ductile brittle transition, stress concentrators, and fatigue in aluminum steel, and their impact on ships and airplanes. In order to understand the mechanical properties of a material, we must first look at the material's atomic structure in the form of a unit cell. According to the textbook cited, a unit cell is the basic structural unit or building block of the crystal structure. Whenever a tensile load is applied to a material, the bonds inside the material are in a state of tension so as to resist the tensile force being applied. Whenever a material's tensile strength is exceeded, deformation occurs. Deformation either takes the form of elastic or plastic deformation. Shown here, we can see the differences between these two types, and that elastic deformation allows for the bonds to be stretched and return to their original shape. However, plastic deformation is where the bonds are stretched and the atom planes inside the unit cell are sheared. Due to the plane shearing, the material does not return to its original shape, resulting in permanent deformation. Inside of a material atomic structure are things known as grain boundaries. When a tensile load is applied, the more grain boundaries present, the harder it is for the planes to shear, making the material stronger. Temperature affects grain boundaries in that when heat is applied, it causes the grain boundaries to merge together, making the material more ductile. The opposite is true when temperature is lower, and that the grain boundaries become stiff, making the material stronger, but also brittle at the same time. This process is known as ductile to brittle transition. As you can see here, as temperature increases, ductility increases, but whenever temperature decreases, a material becomes more brittle. In some steels, the ductile to brittle transition temperature is around 32 degrees Fahrenheit, and in some aluminums, it's around negative 425 degrees Fahrenheit. At its specified ductile to brittle temperature, a material will transition from a ductile to brittle state, and vice versa. Another flaw type is stress concentration. Stress concentration occurs at cracked tips and sharp corners. As seen here, when a force is applied to a material, stress concentrates at these points, making it easier for cracks to propagate through a material. An example of these two flaw types are Liberty ships. During World War II, America mass-produced warships called Liberty ships, which were assembled by welding low-grade prefabricated plates of steel together. When these ships sailed in the waters below the ship's ductile to brittle transition temperature, steel became brittle, and due to the stress concentrators at the corners of the steel plates, cracks started to form in the ship's hull, resulting in a few of these ships cracking and splitting completely in two. Our final flaw type is fatigue. According to the textbook cited, fatigue is defined as the level of stress at which failure will occur for some specified number of cycles. It is similar to wear and tear, and that after continued use, a material will begin to form cracks leading to fracture. This is more of a problem in aluminum than it is in steel, and that, as this chart shows, at a specified load, steel will not experience fatigue despite the number of cycles of stress. However, this is not true for aluminum. This causes problems for planes in that each time a plane cabin is pressurized and depressurized, it undergoes fatigue in the form of cyclical stress, allowing for cracks to form. An example of this is the de Havilland Comet. In order for jet travel to be efficient, a jet has to fly at higher altitudes. Engineers of the de Havilland Comet overcame this by pressurization of the plane's cabin, making it possible for the passengers to breathe at higher altitudes. However, due to the continued pressurization and decompressurization after each use, the planes began to experience fatigue, and this was very problematic because as a result of stress concentration at the corners of the square windows, cracks started to form around these points, and after continued use, the cracks became large enough and eventually caused the de Havilland Comet to disintegrate mid-flight. For this reason, all of today's airplanes have circular windows because they reduce the amount of stress on an airplane's windows by equally distributing the stress around the circle instead of concentrating it at square tips. So knowing all this, we can see how flaw types such as ductile to brittle transition, stress concentration, and fatigue in aluminum steel can have huge implications on the overall use of and safety of ships and airplanes, and that even small details such as the shape of window can be very important.